Okay, so far we have looked at how forces can be broken up into two different components, the x and the y component if we're only focused on two dimensions. And now we're going to look at the effect of forces in terms of their ability to rotate bodies. Right? These two components can translate bodies, but what about their ability to rotate? Right? And this little diagram that you have down here below is going to be something that we're going to come back to. There's a vector component way to do this, and there's a scalar way to do this. We'll use both eventually. Well, let's first talk about the context for what's going on and why we care. Usually people introduce this concept when they talk about a lever arm. Here we have a cheater bar that's trying to open up this valve on this tank that's sitting here. And so how do we quantify this force of this person pushing down on the bar and what that translates into in terms of trying to rotate this little nozzle or nut on the nozzle? Another common application would be where we take a cruciform tire iron and we then put two different parallel forces of equal magnitude on it. That's going to create also a rotational effect. Now, looking ahead a little bit, we have two different ways that we might try to represent that rotational effect of those, what we'll learn to call a couple coming from two forces. And so some people like to attempt to show the arrow that indicates the rotation, but that gets a little confusing to try to see the 3D. And so what people have often done for a long time is use the double-headed arrow. Single head means a force, a translational effect. Double-headed means a rotational effect. So if you take your right hand and put your fingers around in the curl of the direction of that effect, then your thumb is going to, on your right hand, show you the direction that of the double-headed arrow. Right? We'll be coming back to some of that vector notation in a bit, but one of the first things that we're going to really tackle is how to quantify this lever arm kind of concept as well as the force couple concept. And eventually we'll start looking at things like equilibrium of cranes and all kinds of things that will use this moment effect. Right? And so here's a situation with a tower crane lifting up things at a construction site. And so as it's trying to lift up these structural members, then the weight of those structural members imparts a force that wants to try to rotate this tower in a direction that would be counterclockwise. Whereas with this ballast weight here, which is used to try to counter the effects of what you're lifting, then you'd have a rotational effect in the other direction about this pivot point. A lot of folks get the sort of physical idea of what this rotational effect is all about. What they struggle with a little bit is that these forces have rotational effects about other places too. That and we'll talk about the moment of a force and how we selectively calculate that moment about various places on the structure, usually in order to find a reaction someplace. Right, so let's go back and now briefly define just what it is, how we quantify this rotational effect, this thing called a moment of a force. Is going to be quantified by the magnitude, and by the way we'll use m. People want to say, well, that's a torque. Well, no, torque is a subset of moments. Moments are a far more general kind of thing. We can impose forces on that cheater bar. That cheater bar creates a moment that turns out to be a torque on the nut. There's a sort of a load path thing going on there. If we're really careful about this, the moment of a force is kind of like a torque. As I say, torque is a subset, but it does create a rotational effect, tendency to want to rotate things. And so if we have a line of action of this force that's passing through point B, the magnitude of this moment with respect to point A is just going to be this scalar distance d times the magnitude of that force. Now I'm trying to be a little bit more careful using the vector notation. It's just the total magnitude is equal to the perpendicular distance to the line of action. Right, that's going to be a key thing. It's just not any distance, but it's that perpendicular distance. It's convenient in a lot of ways because it creates a little right triangle for us. Now from a pure vector notation standpoint, we could describe this as the moment at A is equal to this position vector cross the force vector. Right now, the cross product is something we'll work with at another time. We're going to predominantly focus on the scalar representation because we're going to be in 2D, and oftentimes this vector notation approach is most convenient when you have more complicated situations, but particularly in 3 dimensions. So I don't want to spend too much time on that, but rather I instead want to focus on the scalar representation. Right now, what happens here from a big picture standpoint, the cross product takes care of finding out what this perpendicular distance is for us, and it's even more powerful than that because in reality the position vector only has to go from the point that we're interested in to anywhere along the line of action in order for us to capture what we want. So it's a very powerful tool that turns out to be a little bit more complex than we really need it to be for most of our 2D problems. Right? So in the next whole series, there's about 5 of them, of examples that we're going to explore. We'll demonstrate just what the heck this really means, how to calculate it in a whole lot of different situations, and get into some specialized situations such as that cruciform tire iron and some things like that.